Lasso seems to work, and point out some problems with it. I will also talk about the so-called double lasso, and I will remind. I hope you saw in 482, but if you didn't, I will remind you and I'll give you a reading on it. One is the Fritzsche level trick for handling dummy variable regressions. We're going to use a variant of that in what's called the double lasso. Now, I'm going to skip some things that are in the book, and that's because even in the last 2 or 3 years, we've learned that the approaches in the book in chapter 6 in particular really don't work that well. So I'm not going to cover forward stepwise regression. You need to read it so you know what it is, and so you can say, well, we don't do that anymore because we do double lasso, and here's why. Backwards stepwise regression, in fact, all of the stepwise regression we're not going to do. We're also not going to do dimension reduction using principal components analysis. And I will talk about that later on. Is Herbert on? Herbert, are you there? Looks like there are people in the waiting room, and I've got to. Okay, as I was saying, I'm not going to cover principal components analysis for data reduction. I am going to talk a little bit about partial least squares, but not because you should do it that way. It's because I'm going to give you a method of selection, which is a pre-lasso. They're called safe methods. And when you see the safe methods and then read the section in chapter 6 on partial least squares, you're going to go, oh, that's very similar. So let's get right down to work. Remember, we started this course talking about if you have very complicated models, you'll tend to overfit. And so what we want to do is we want to find some way of simplifying them. We call that model selection. And most of the models, until we get to neural nets that we're going to look at, can be put in a regression framework. Maybe that's not ideal, but can be put in a regression framework. And so I'm going to talk about regression frameworks and simplification. And we've talked about that a bit already. So we have a model of the form y equals x beta plus an error. And let's say that those x's, that there are a huge number of x's, so you don't have very many degrees of freedom. But even if you have a lot of degrees of freedom, if you have a whole bunch of x's, you've got a problem. And what we're going to do is we're going to look at y minus x beta transpose y minus x beta. This is the sum of the squared residuals. And then what we're going to do is we're going to penalize ordinary least squares for being too complicated. And what we're going to do here is we're going to add a penalty for complexity. And it's going to be of the form g of beta. And so let's talk about some of the possible g of betas. So one would be the number of non-zero beta. Okay. So if you have too many non-zero betas, I punish you. And G could have some scale terms in that, but basically it's going to be the number of non-zero betas. 2, we could look at summation I equals 1 through P, absolute value of the beta i's. That is, we could look at the lasso, okay? And this, it turns out, penalizes things for being too complex, as you will see later today. 3, perhaps not so clear, is we can have summation I equals 1 through P, beta I squared. That's the ridge penalty. And we can have other kinds of penalties. For example, I could have summation I equals 1 through P, beta I better make it an absolute value, to the 1.5. Okay? That's something I could do. Something that's often done is something called the elastic net. The elastic net looks something like alpha, the summation I equals 1 through P, absolute value beta I, plus 1 minus alpha, summation I equals 1 through P, beta I squared. So it's a combination of the lasso, of the ridge and the lasso. And there are all sorts of other methods. And so you're going to read papers and they're going to say, here's how we regularize this. And there's going to be some tuning parameter lambda, and then there's going to be some penalty for complexity. And then usually the paper's going to explain, we chose this one for the following reason. It is impossible to go through all the possibilities, but the most important thing is that what's going on here is I'm penalizing my optimization for having too many parameters or being too complex. Okay? So there's some details here we need to go through. Uh-oh. This isn't good. Try this. So the first thing we're going to do in terms of details is we're going to change our data a little bit. So I have y equals x beta plus an error. And you notice I never put the intercept in there. Now, one reason for that is I can have a column of x's being all ones. But I'm not going to do that. Instead, the first thing we're going to do for machine learning models, not for inference, but for machine learning models, is I'm going to normalize my data. What do I mean by that? I'm going to take y minus y bar over the square root of the sample variance of y, and I'm going to make that my new y. And then I'm going to take each x, xi, minus xi bar over the square root of the variance hat of xi. And that's going to become xi, where here I indexes the variable, not the observation. So basically, I take each one of my variables in the model, and I subtract off the mean, and I divide through by the standard deviation. Now, I'm going to explain why I do that as I go along. So we first normalize the data. And I'm going to talk about the lasso, but I will come back and I will compare it with the ridge. And so now we're going to look at min beta y minus x beta transpose y minus x beta plus lambda, the summation I equals 1 through p, absolute value pi, beta I. Now, what does this normalization do? Well, it turns out if you have an x that's in billions and billions and billions of units, and another x that's in just tiny little units, the lasso will tend to pick up on the one that has the units billions and billions and billions and toss that out. And so you don't like that. You want the variables to be treated symmetrically. And so you normalize your data so that doesn't happen. Now, another way of doing it is to have a different lambda for each different beta, or for groups of beta. And that makes sense sometimes, but normalizing your data by and large lets us fairly safely do the lasso. Okay. So we want to minimize this. And how do we do that? Okay, well, we pick a lambda and solve. Well, how do we pick a lambda? And I hope by now you know it's going to be k-fold cross-validation. Okay, so to find lambda, use k-fold cross-validation. So let's go through the steps we're going to do then. Now, sometimes you want to start with lambda equals 0. If you have lambda equals 0, that gives you the ordinary least squares to start with. But oftentimes, you're not going to be able to do that. So what if you have more more variables than you have observations? And it's very easy to make that happen. In the next lecture, where we move beyond linearity and start talking about, basis functions and splines and stuff like that, very quickly you get way too many variables, way more variables than you have observations. So you can't do ordinary least squares in many cases. And so I don't start usually at 0. I pick some lambda, and then I move on both sides of that lambda. So we're going to choose a lambda. Okay. we'll go a step back from that, just so we're clear here. Divide data into K roughly equal groups. I'll just mention something. It is never the case that you will need more than one observation difference between any of the groups. Okay, so you can get them all within about one observation of one another. Think about that for a bit and you can see how that happens. Okay, now we choose a lambda. And we'll just call this lambda 1. Okay. And estimate Lasso on the 2 through K groups. Compute SSR using the test group, that is group 1. Okay. Repeat for all K groups. And so for lambda 1, I have 10, or I have K SSRs, or K test SSRs. Okay. Average these. And it's also useful to calculate a standard deviation for them as well. Okay, so compute the standard deviation for these as well. Okay, so we've done that for one lambda now, and now we're going to do it for another one. Okay. So I'm going to start plotting this. And you've already seen this before, but I want to go through it again with the lasso. And so here we have lambda. Here we have the sum of squared errors. Or maybe because if the things are not exactly equal, we should do the mean square error. One observation shouldn't make a difference, but let's do mean square error. And let's say here is lambda 1, and there is the mean square error for that. I'm going to pick a lambda 2. Okay? And I'm going to repeat what I just did with that fixed lambda 2. And I might get something like that. And if I got something like that, I would go back the other way. Lambda 3, and I might have something like that, and a lambda 4, and I might get something like that, and I'd probably go in here for a lambda 5, and maybe I get something like that, and I have the standard errors at each one of those points. So those are the mean MSEs, and then at each point, you're going to have a standard error around them. And then what I'm going to do is I'm just going to fit a curve to these. Okay? And I'm going to say the bottom of this curve is right here. That's my lambda star. That's what I'm going to use as the lambda. Okay? Now, when you use HDM, which is a package we're going to start using next time, which does a lot of the same things that GLM and GLMNet do. They don't like k-fold cross-validation. So they actually calculate a formula for lambda. And there's some debate about which is the best to do. Whenever there's a debate these days, what I do is I use them both and just see which turns out the best out of sample. Okay, so that's how we get our lambda.
I have a quick question.
Sure.
So you say we want to like divide data into k equal, like roughly equal groups, and then so that's basically like for this type of questions, like what you just did. So k is basically equals 5, basically, because you have like
10. I usually do 10, but 5 is okay too.
Oh, so like then what? Like how should we? So how many times we should try for lambda? Is there like a typical way we can do?
No, so we divide it into k equal groups randomly. Okay, no overlap. Okay, and then we just start going through the lambdas, and all I do is I take enough that I can see, you know, the minimum seems to be in there somewhere.
So when
and then I just fit a curve through there. You could do it with a regression. You could do it with curve fitting. You can just eyeball it.
So there's no like a typical number for how many tries, but when you see actually like a U shape with like some minimum.
Yeah, that's what I do. Now, for those of you who've taken an optimization course, you could imagine doing golden rule search on this. So you could do exactly what we talked about in line search, and you could do golden rule search. I think that's overkill, but you could certainly do that. You could certainly do that.
That makes sense. Thank you.
Now, why does this work? How does this reduce the complexity of the model? And you can find this picture in the book. I also put a note for those of you who don't remember or haven't looked at Lagrangian multipliers in the past. Talk a bit about those sorts of things. But here's beta 1. Here's beta 2. There's 0, 0. Okay. And as it turns out, and I'm going to say that this distance from 0, 0 is S. Okay? So the distance to all those points is S. So this point down here would be minus S and 0. This point here would be 0 and would be minus S and 0. This would be 0 and minus S. This one up here with S is going to be 0 and S, and this one over here is going to be S and 0. So it turns out that's going to be the constraints that we're going to talk about in a minute. And now I'm going to put in the contours of least squares. So this point, if it exists, is beta 1 hat, beta 2 hat, the OLS. And you note right here that the curves, the level curves, touch that diamond at beta 1 equals 0 and something in here. Okay. By the way, it doesn't have to be less than S. I could have done this in such a way that it didn't turn out to be. Oh, I guess I couldn't have. So the point is that beta 1 is set to 0 here. And beta 2 is biased towards 0. It's between S and 0 or minus S and 0. Okay. So this is what makes the lasso work. So let me give you some theory here, just a tiny bit. I could look at two problems. One, min beta, y minus x beta transpose y minus x beta. Subject to the constraints that the summation I equals 1 through p, absolute value beta I, is less than S. Okay? And my claim is that the graph let's say this is 0, 0. The graph of that set looks exactly like that diamond. That is, this is minus S, this is S, this is minus, this is plus S, this is minus S. Okay? And the solution will either be at a vertex or it will be tangent, just like in consumption and production theory. Okay? It turns out there is an area of mathematics called duality, and you've actually seen this. You probably don't realize it. You know how you can minimize costs subject to a production constraint? It turns out if I have that cost function, I can very simply work backwards and tell you what the production function had to be. There is a duality between cost and production. Similarly, there's a duality between this problem and the lasso problem. That is, for every S, there'll be one and only one lambda. For every lambda, there will be one and only one S. And so you could decide to solve whichever problem you wanted to solve. And you always do that in such a way that it's numerically the easiest. Numerically, it's the easiest to solve the Lasso form that we've been talking all along here about here. But to have the zero, you really want to look at what I wrote down before. I am getting a warning here that my internet connection is unstable. So I will keep an eye on it and hope it doesn't crash on me. So let's take a quick look at the ridge regression. Recall the ridge regression was of the form y minus x beta transpose y minus x beta plus lambda, the summation beta I squared. And it turns out the problem that's dual to this, we use the term dual, is minimize y minus x beta transpose y minus x beta, subject to the restriction that the summation of the beta I squared is less than or equal to s. And again, for every s, there's a unique lambda where the betas in both problems will be the same. Let me put min here. Okay. So if I have a solution to this problem, that is, I have betas that solve this problem for a given s, I can find a lambda up here where the betas that solve this problem are identical to the betas that solve that problem. And so again, I can graphically work with this, analytically work with this. And so let me show you what that picture looks like. And I'm going to make this 0, 0. Okay. That's supposed to be a circle with radius s. And again, the solution is where the level curves for the sum of the squared residuals just touch the constraint set. Again, this set in here is beta 1, beta 2 hat, the LLS. And so the ridge solution would be beta 1 ridge hat and beta 2 ridge hat. Do it the other way around. Ridge. Okay, right here. Okay. And you can see that these have been sent closer to 0. All of these estimators are called shrunken estimators. And these are called shrinkage estimators. And until we really started understanding what was going on, we thought it had to do with the shrinkage. What it really has to do with is it is making the models less complicated. It's making the models less complicated. It doesn't seem so here, but I think you see it with the lasso. With the lasso, it actually sends coefficients to 0. So let me state something really sloppily here. There's a formal way of doing it that won't make any sense, but when I state it this way, it's fine. And then some of you would go, wait a minute, we're not Bayesian. That doesn't make any sense. Okay, so it's kind of a theorem. If the lasso sets variables to 0, and I should say the coefficients of variables to 0, then with very high probability, those coefficients are actually 0. Now, here's the problem. Coefficients are fixed, okay? So there's no probability that they're 0 or not 0. The things that are random are the lasso, okay? But you see what I'm saying here is, that is, if the lasso says the coefficients of certain variables are 0, then you can be pretty certain those variables don't belong in your regression. You've just done model selection here. Okay. Well, this is just great. Okay. This is just great. This is easy. It's simple. It works well. So what's the problem? Well, there are a couple problems. One of the biggest problems is the second part of this. And all of the other coefficients are biased towards 0. What does that mean? It means they're shrunken. Okay. So if you tried to test the hypothesis that something was equal to 0, and you found that you couldn't reject that hypothesis, it might be the case you couldn't reject the hypothesis because the coefficient was biased towards 0. It actually wasn't really 0. It was just biased towards 0. Okay? So this makes things very, very hard if you're trying to do inference. Now, on the other hand, if all you're trying to do is predict, and predict well out of sample, this works fine. You don't really care about the coefficients. But as I've said in the past, you know, you go on the elevator with Jeff Bezos and you say, you know, we're going to lose 10% revenue next quarter, and you know that my model is never wrong out of sample. He's not going to say, what a cool model. He's going to say, why is that happening and what can we do about it? And the why is it happening has to do with what the coefficients are. We'll talk about what to do about it later on. Those are so-called counterfactual statements. Okay.
Could you explain again like the second part? So like the first part is setting like those the coefficient, they're probably 0. So you mean the rest of like the coefficient that's not 0 are biased?
Are biased downwards towards 0. So they'll be smaller in absolute value than they really are. So they'll be biased downwards. So ordinarily when you do a regression, if the Gauss-Markov assumptions hold, then the coefficients are best linear and unbiased. That is, they're centered at their true values. Here, these are going to be centered at a value closer to 0, so everything's going to be biased towards 0.
But isn't then, if we try to like explain like what's the like the factor of things, since all of them are shrinkage, but the compared to other, it's still like bigger than 0. Isn't we can still like do like an order, like the order still apply, isn't it?
The order might still apply, but let's say that one of these coefficients is a marginal cost, and you say, I want to set price equal to marginal cost, and you say, that's the coefficient on output, and it's 0.3, and so you charge 0.3, and it turns out that was way too low a price.
Okay, understood.
Yeah. So what the lasso gets right is which of these things are actually 0. What it doesn't get right is the magnitude of the other ones. So what do we do? It actually turns out to be relatively simple. So this is due to two of my colleagues, Alex Bayoni and Victor Chernozukov. Alex is a professor at Duke. He's an Amazon scholar, and he's here full time. And Victor Chernozukov is a MIT professor. He was at Amazon for 2 years as an Amazon scholar, and he still works with us part-time. And what they came up with was the following. 1, do a lasso. Okay. And note the variables kept by the lasso. Okay, so these are the ones that weren't set to 0, or whose coefficients were not set to 0. Second, do OLS of unnormalized y on unnormalized x's that were kept in step 1. Remember, up to now, you've been working with normalized data. Okay. Now we're going to go back to the unnormalized data. But if variables 1, 5, and 9 were kept, then we go to the unnormalized 1, 5, and 9 of the x's, and we run a regression of unnormalized y on unnormalized 1, 5, and 9 x's. Okay. Theorem. If n is large and p is small relative to n, then OLS in the second step has exactly the conditions that it would have if you knew in advance which variables to include. Now, since you guys probably haven't done a lot of this, you don't realize what an astonishing result this was. I spent my early career trying to solve this so-called model selection problem. So you have some method of selecting a model, and then you had to account for the type 1 errors you would make as you were going along. Remember we talked about false discovery rate problems or multiple comparison problems. And people struggled with this for at least 100 years. And nobody came up with a solution until Victor and Alex came up with it. It's a really, 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 really neat result. Okay. Now, there are problems, and you should be asking yourself, this is great. How big is n large? This is great. How big is p small? Okay. So p being small relative to n is called a sparsity assumption. And there's really no way of checking this. Okay. If you really knew how small p should be, by the way, this is the final p, not the p you start out with. So if you know only a handful are going to end up mattering, then you can do this. Okay? But you often aren't going to know that in advance. And so this was a really cool result, but people were worried about it. People worried about it for a long time. And then Victor and another one of his students, Chris Hansen and Esther Duflo, who got the Nobel Prize last year with her husband for development economics. It turns out she's also a top-tier econometrician. And Whitney Newey, who is a top-tier econometrician, and they're all at MIT. I think Chris is at the University of Chicago now. And they came up with a solution to this called the double lasso. And the double lasso right now is what I recommend everybody use for model selection. However, before we get there, we're going to have to cover two other things. The first thing is called the Frisch-Waugh level trick. And I hope you've seen this before, but my guess is probably not. And the second thing is I'm going to show you safe model selection. And we just learned model selection, but I'll talk about what the problems are. In fact, I think I'll do it in the opposite order. I'll just talk about the safe model selection first. Okay. Now, the lasso works even if you have more variables then you have observations. Now, in ordinary least squares, that won't work. And in that situation, if you had, let's say you had billions of observations, and you had many more billions of features or independent variables, lassos are going to take a huge amount of time. Just a huge amount of time. And so people started asking, is there some quick way we can eliminate variables that we know are not going to show up in the regression, not going to show up in the lasso at all? And the answer turns out to be yes. Okay? And these are called the safe methods. Okay. And I'm going to give you the simplest of these, but there are many of them. They get more and more complicated. But if you run into a problem where things aren't working, you want to dig these up. And I'll put some readings about these, but you can find them online. So at least one of my honors students ran into a problem where she simply was not able to do the lassos. Right? One lasso was taking her 3 weeks. That was for one of the folds. So that's 10 times 3 weeks to get through one lambda. And then who knows how many she was going to have to try. Let's say it was another 10. You know, she's well into the next year. So how do you handle that? Okay. Well, it turns out that there's kind of a really interesting approach. This is due to a guy named El Gahuri at Berkeley. He publishes in incredibly weird journals, so you pretty much won't find him. He's an electrical engineer and he does signal processing. And so he developed this for that, and he published in a journal that you wouldn't know whether it's well known or not. It's not well known at all, called the Pacific Journal of Optimization. And it just kind of sat there, and every now and then somebody would say, yeah, this guy at Berkeley says he's got this solution for this, and nobody can find the paper. Well, eventually we all found the paper. So this is how it works. Okay. One, again, normalize your data. Realizing that eventually we'll come back and unnormalize it. Note this means that y bar equals 0, variance of y equals 1, xi bar equals 0, variance of xi equals 1, where the i's indicate the variable, not the observation. Okay. Compute I equals 1 through p, and I'm going to call it the correlation y xi. It turns out, since we normalized everything, this is simply the inner product. Okay? Well, you know how to calculate correlations. Now, notice I'm not doing anything very tough here. I'm just calculating a bunch of correlations between y and each of the x's. I'm not calculating correlations between the x's. I'm just calculating correlations, and so there's going to be p of them. Okay? And then I'm going to set CI equals the absolute value of y transpose xi, or the absolute value of correlation y xi. Okay? So that's easy to do. Okay? I'm going to set lambda star equal to the max of the CIs. So it's the largest absolute correlation you find in there. Okay? And then I'm going to calculate a threshold, T. Okay? And this is going to be lambda, where lambda is the lambda that you're using for your lasso. Okay? Times 1 plus 1 over lambda star minus 1. So lambda star is the max CI. Did I do that right? Yes, I did that right. And lambda is the lambda that you're using for your lasso. Okay. And then set beta hat I equal to 0 if CI is less than T. Okay. So this says I calculate these correlations, I calculate this threshold for my lambda, and then I set beta equal to 0 whenever this absolute correlation is less than the threshold. And what I can show you is that if you had done the whole lasso, anything that this sets to 0 would have been set to 0 in the lasso. Okay? Subtlety here. Even though that's the case, it is not the case that this safe model selection finds all the ones that are 0. What it does do is anything that it says is 0 is going to turn out to be 0. So what does that mean? So that means you do the safe model selection, okay, and then run a final lasso on the variables not eliminated. Okay, and that's going to eliminate some more variables. Okay, and then that final lasso, you're back into the Bayoni-Chernizukov world, and you say, well, then what I can do is on the unnormalized data, just run a regression of y on any of the variables that weren't eliminated either in this first step or in this second step. I can assert to you, because I've done it, that doing this safe selection first sometimes increases the speed of the final lasso or the whole analysis by 3 orders of magnitude. That is taking things from weeks down to minutes. So it's really, really, really useful. That said, it doesn't always work. Sometimes it won't eliminate anything. Okay. There are other safe model selection procedures. and I'll give you some readings on them. This is an area that's developing now, and it's going to keep developing. There is also another set of model selection or screenings. So these are called screenings. You screen, get rid of what you can get rid of, and then run a final lasso. And these are called the strong methods, and they're due to Bob Tibsorani, Trevor Hasty, some of their students. I think Bob's son Ryan, who's now a professor at Carnegie Mellon, was involved in this too. They're called the strong methods. And so you'll see people using strong methods. The problem with the strong methods is the strong methods sometimes throw variables out that shouldn't be thrown out. Low probability, but it can throw those variables out. So it will throw variables that shouldn't be thrown out, we'll throw them out. And if you're doing inference, that is, if you're trying to test hypotheses in a final a regression after lasso, you're going to be dead in the water if it threw out one of the important variables.
So when you're like saying this is like the safe variable elimination, so are we like doing it to eliminate variable? So like when you're saying it's like safe, are we trying to like eliminate all the data that should be zero as is safe, or are we trying to eliminate not affecting other coefficients?
No. So we're trying to eliminate anything that's going to turn out. So I could imagine doing the whole lasso, okay, and it takes weeks.
Mm-hmm.
Okay? Or I can do this safe selection, and it's going to say, here a million variables that are not going to show up in that big lasso.
Mm-hmm.
So you can already throw them out. And now on the variables left over, do the lasso, and you'll end up with the variables that you would have had you done the big lasso. So this is a two-stage procedure where you throw things out that you know that are going to be zero, and then you let the lasso take care of the ones you can't tell for sure.
Okay. So it's like saving the running time for the lasso.
Saving the runtime. You'll get exactly the same variables. Let's be careful here. The safe procedure will throw out a bunch of variables.
Mm-hmm.
The lasso would have thrown those out too, with probability 1.
Uh-huh.
Okay? The lasso may throw out some others as well, but you already threw a whole bunch out, so you're speeding up the time. Remember how we optimize the lasso? Maybe I didn't say this. We tend to do coordinate-wise minimization. Very, very slow. And so the faster we can make this, the better. So it's a two-stage procedure. You end up with exactly what you would have ended up with after the final lasso. You end up with what you would have ended up with if you'd run that big, huge lasso in the first place. Okay. But here you just do it in 2 steps. One, where all you're doing is looking at correlations and going, okay, that's out, that's out, that's out, that's out, that's out, which is a really simple thing to do.
Okay, that makes sense. Thank you.
And if all we were going to do was the lasso, we could stop there. Okay? But we want to do OLS after lasso so that we can do inference. And as I mentioned, the theorem says you kind of have to be lucky. You have to have enough observations and most of the variables have to be 0. Or most of the coefficients have to be 0. There's true sparsity. And you actually have to be able to write down a formula for that sparsity or a bound for it. what people found was in very high dimensional situations, even with large degrees of freedom, there was a problem that you would get a bias. And people wondered about why there was that bias and whether it could be eliminated. And so I'm going to go a little detour here. And the detour is going to look at two things. I'm assuming you've all seen the omitted variable problem, and I will go through that a little bit. And then I hope you've all seen the Frisch-Gauss level theorem, but I know that some of you haven't. So let's start with omitted variables. And I will tie this back into what we're doing here, because essentially what we're going to do is, well, I'll show you. So I have y equals x beta plus z gamma plus an error. And going forward in the rest of the course, when I do a regression, I'm going to assume that I have at least subtracted the means off the y's, the x's, and the z's. So not necessarily divided through by the standard errors, but at least subtracted off the means. If I do that, it necessarily eliminates the constant term. So the constant term is eliminated by demeaning every one of the variables. Okay? So here's my model. Okay? And let's say I regress y on x, ignoring z. Okay? So beta hat in matrices is x transpose x inverse x transpose y. That's x transpose x inverse x transpose, and now we're going to plug in for y, x beta plus z gamma plus an error. And ordinarily, you don't have that z gamma in there. Ordinarily, that z gamma wouldn't be in there because you haven't omitted any variables. But here we've omitted some variables. And so this turns out to be x transpose x inverse x transpose x beta plus x transpose x inverse x transpose z gamma plus x transpose x inverse x transpose epsilon. Okay. And so let's look at the expected value of beta hat. So E beta hat is equal to, well, what's this? X transpose X inverse, X transpose X. That's the identity, so that's just beta. Plus the expected value, X transpose X inverse X transpose Z times gamma. Okay. Plus the expected value x transpose x inverse x transpose epsilon. And let's do all these expected values conditional on x. When I do that, I'm going to get beta plus x transpose x inverse the expected value of x transpose z given x, gamma plus 0, assuming that the model y equals x beta plus z gamma plus epsilon was the correct model. Okay? So that means we've got a bias here. Okay. So what's the bias? It's X transpose X inverse, and I'll even write it this way, X transpose the expected value of Z given X, gamma, okay? So, when is this equal to 0? Well, if gamma is equal to 0, that means that Z doesn't belong in the regression. So, if Z doesn't belong in the regression, leaving it out doesn't hurt it, clearly. When this happens, we say that the Z's weren't important. What else is it equal to 0? If the expected value of Z given X is equal to 0. Okay. When does that happen? That happens when Z and X are uncorrelated. When Z and X are uncorrelated. So, if Z doesn't matter, or if Z matters, but Z and X are uncorrelated, that is, what you left out is uncorrelated with what you put in, then you don't have an omitted variable bias. This is key for what we're going to do next. What we're going to do is we're going to arrange things to force this to happen. We're going to arrange things to force this to happen. By the way, I can't tell you the number of times people will say, yeah, I was only interested in those two variables, so I only ran a regression of y in those two variables. Why are you complaining about these other things I'm not interested in? It's because you've got an omitted variable bias. That is basically what's going to happen is the coefficients of those two variables are going to pick up the effects of the fact that there was correlation in the error term. Well, let's put that model back up again. Okay. And let's say that I was only interested in beta. Okay. I'm only interested in beta, and I would like to find a way of just estimating beta. And here's a way of doing it. What? Regress y on z. Get the residuals yz. Notice there's no x here. I'm interested in x, but I ran a regression of y on z. 2, regress each x on z, get rxz. So if x is n by p, Rx is also going to be n by p. Okay? 3, regress, whoops. Ryx, Ryz, pardon me, on Rxz, get beta hat. that beta hat will be identical to the beta hat you would have gotten if you had done the regression on the whole thing. Identical, numerically identical. Epsilon hat will be identical to, and I'll write it this way, RYZ minus RXZ beta hat. That is, the ordinary least squares residuals that you would have gotten from running the whole regression will be identical to the residuals you get from running this simpler regression. And finally, SSR will be the same as well. So the sum of squared residuals. Problems here? Degrees of freedom are off. Why? Because you need to take into account you actually did do some estimation to get the z's. So if the z's have k parameters in them, your degrees of freedom are n minus p plus k. Whereas when you do this regression down here, the computer doesn't know that you did the first stage regression. It's going to say your degrees of freedom are n minus p. And so you will overestimate your degrees of freedom. Similarly, your mean square errors, if you divide by degrees of freedom, will be wrong as well. Now, when do you use this? You use this when the regression of x on z is really simple. So it turns out that if z are all dummy variables, then that regression turns out just to be the means of each one of the x's. Very easy to calculate. I shouldn't say the means, the group means. Let's just leave that aside. I'll give you an article to read on it. The point is, you do this when this second regression is very, very simple and very, very fast. This is called the Frisch-Waugh level trick. So Frisch got, I think he got the first or second Nobel Prize. He was a very early time series guy, did all sorts of cool work in the mid to late 1930s, and then World War II and all that kind of stopped his work for a long time. Waugh was one of his students, and this was before the days of computers, and so they were always trying to make things faster. Okay? We've dug all this stuff up because with the huge data sets we have now, those tricks turn out to be very helpful. In the 1980s, we didn't really need them. Computers were faster than anything we could imagine. And it really isn't until about 1995 with the, essentially with Google, where all of a sudden you're dealing with petabytes of data per second. And you've got to find some way of analyzing them. You have to find some way of saying, this is in fact the search term that Greg Duncan was looking for, and here's where he's got to go. And so all of these computational tricks have come back to the fore, and I think they're going to be around forever. So the two things we talked about here, which don't seem to be related, but they are very related, are the Frisch-Waugh level trick and omitted variable bias. So just keep that in the back of your mind. This is more about why the double lasso works. What you really need to know is what the double lasso is. So when you're doing a regression analysis, when you're doing testing, you're supposed to specify the hypotheses you're going to test in advance. You're not supposed to do the going through and seeing what's significant and what's not significant and say, there's a hypothesis I can do. That's just data snooping and it's wrong. You're going to be committing those type 1 errors. You're going to have a multiple comparisons problem. So we're going to agree in advance what hypotheses we're going to test. And we're going to have a model that looks like this. Y equals X beta plus Z gamma plus an error. And here, we're going to do something a little bit different. The X are focal variables. Okay? These are the variables you're interested in. These are the variables you want to test. Oftentimes, it'll just be one. Oftentimes, it will be treatment in an experiment, in a treatment and control experiment. Oftentimes, it will be the effect of a policy, a dummy variable. It will just be one variable. But oftentimes, it can be more than one variable. Okay? So these are the ones you're interested in. The Z are nuisance variables. We don't care about them. But why do we need them? To avoid a omitted variable problem. That is, if I were just to run the regression of y on the x's, and if the gammas mattered, or if the z's were correlated with the x's in any way, then I would get a bias if I ran a regression of y on z. Okay? And so what we're going to do now is something a little similar to what we just did. Okay? One, a lasso of y on z. Okay? Note variables kept. So some will be eliminated and some will be kept. Okay? So this is telling you which of the variables y are important. Okay? 2. For each x, lasso x on z. Note variables kept. Okay? The variables kept, the z's that are kept, must be correlated with the x's. the z's that are not kept are not correlated with the x's, so we can throw them out. And so what we're going to do then is we're going to note, I'm going to say 3, let z star be the variables or the matrix of variables kept in any of the lassos. Okay. So we have our focal variables x, nuisance variables z, lasso y on z. Some variables are kept. For each x, lasso x on z, variables are kept. Get a final set of variables kept in any of the lassos, and now here's what we're going to do. OLS y on x, which we care about, and z star. Okay. This regression has accurate tests and estimates. The coefficients on the betas and the z's are not quite unbiased, but they're consistent. What do I mean by consistent? I'm assuming you all done the law of large numbers. It means that if the sample size is large enough, then the coefficients are very close to their true values. Second, the coefficients are jointly asymptotically normal. Third, the f-test on the x's, the usual f-test on the x's in this third stage is correct. Has the right p-value and everything. Okay. This is the correct way to do model selection. This is the correct way to test. It's called the double lasso. There's also one for logistic regression, for multinomial logistic regression, for Poisson regression, which we haven't talked about, and for anything in what's called the generalized linear model. It's really, really, really a neat result. Now, I have to say for those other things, it's not as simple as a lasso on everything, but you can do the same kind of thing. And so, while this looks like it's very hard, I want you to read the book, and I want you to see what the book says about model selection. And it, by the way, doesn't say anything about how you test things after the fact. I don't know what econometrics books you guys used. If you used Wooldridge's book, which is a really good book, look on his chapters on model selection, and you're just going to go, oh man, you know, this isn't very good. And at the end, he says, well, you know, you really should take into account that you might have a multiple comparisons problem here, but we really don't know how to do it, so you're on your own. This is how you handle all this stuff. This is relatively new stuff. I was going to say brand new, you know, 2016. Maybe it's 2018 it was published. But it is really cool. And of course, the statisticians are saying, you know, we all knew this, but we always design our experiments so we don't have to do it. And of course, now they're using it like crazy. Just a snide remark there. By the way, I get to do that because my PhD is joint in economics and statistics. So when I want to be snarky to either group, I put on the other hat. So how do you do this stuff? Okay. Well, there's a computer package that you're going to learn. It's very like GLM. It's called HDM, and it was written by Viktor Chernozhukov, Martin Spindler, and Chris Hansen. It's an R package, and you should download it and start playing with the vignettes and everything. But basically, it has something where it's probably R lasso effects. And so what it's going to do is it's going to say, tell me what the effects you're looking for are. Those are your focal variables. Tell me what your other variables are. Tell me what your Y is. And I'm going to run this. I'm going to do all this for you. You're not going to have to do it at all. And things are going to be great. What's the problem? Well, the problem is it doesn't always work. And it doesn't always work for numerical reasons. I'm a really good programmer. Viktor Chernozhukov is a very good programmer. Martin Spindler is a very good programmer. But we are not software development engineers. And I've just been shocked the number of times I've done a prototype which couldn't be any faster if any other human being were doing it. And some first-year software development engineer comes in and says, wow, this is really clunky, isn't it? And speeds it up 100 times. So at some point, I hope they get a software development engineer to do that. It's written in R. You probably like it written in something else, maybe Scala. Actually, I'd prefer it in Fortran or C, simply because those are incredibly fast languages. So as I mentioned to you, I want you to read the stuff on forward and backward stepwise regression, which was an old way of trying to do model selection. Read about principal components regressions, which is an old way of trying to reduce the dimension. Read the partial least squares. Partial least squares is very much like the safe model selection approach, but they didn't have everything pulled together. Okay. So I'll give you a little hint of where we're heading next, and then I'll let you go. Are there any questions about this? The Urminsky paper, Urminsky, I forget, I think it's Chris Hansen and Viktor Chernozhukov wrote a paper for either a psychology or a sociology journal on this. And I think it's the best discussion of this that there is. It didn't get published because it was too hard for the journals in question. And then when they send it to the economics journals said, well, you guys already published 4 or 5 articles on this, and this seems, you know, really not very deep, not very rigorous. On the other hand, you know, we want people to use this, and so we should publish things like that that aren't necessarily the most rigorous things, because not everybody's a theoretical econometrician. So let me tell you where we're going to head next, okay? Staying with regressions, but we're going to make regressions even more complicated. Okay? So we're going to have y equals f of x plus epsilon, where now f of x is nonlinear. Okay. But as it turns out, f of x can often be expanded linearly. And we'll talk a little bit about this. But some of you have seen this. So let's say that f of x, or f takes r into r. And f of x is continuous on, in fact, I don't want it. This is one of those things where it actually does matter. It's continuous on a closed interval. Okay. Some of you have seen this then f of x can be approximated arbitrarily well by a finite degree polynomial. Okay? Finite does not mean small. Finite just means not infinite. Okay? So let's say that it can be approximated arbitrarily well by a 10 million degree polynomial and you only have 100 observations, then you can't learn that function. It's not estimable. Right? Well, you might get a pretty good approximation, but you can't learn all of the coefficients in that approximation. Second, polynomials are really badly behaved. Okay? So linear is not badly behaved. Quadratic's not badly behaved. Cubic, well, maybe it's getting badly behaved. Quartics, quintics, and so on. That is, as the degree of the polynomials increase, you're going to have terms that are just jumping all over. And if you remember your calculus, do you remember as those things started jumping more and more and more and more in a closed interval, eventually you can't take a derivative? Similar kinds of things are happening here. You can take the derivative, but numerically it just doesn't work out very well. So in this case, we have, actually we also have a constant. No, we don't. Yeah, here we'd have a constant because normalizing the x's isn't going to help us here. So we have 1, 2, 3, 4, 5, 6 terms, okay? And a huge number of f's can be written as a linear combination of those terms. Polynomials don't work very well. Well, what other things might we have? Some of you, you should have seen it in 126. I don't know what they teach in there. Certainly, if you did the honors math, you would have seen it. Or if you've taken multivariate calculus. F can be approximated by a Fourier series. That is a sum, an infinite sum of sines and cosines with smaller and smaller and smaller periods. Okay? And again, in that case, any function on minus infinity to plus infinity can be approximated that way. There's another set that we can use called the splines. And what splines are piecewise polynomials. So for example, that's a piecewise polynomial. It's piecewise linear. That could be piecewise quadratic. I could do piecewise cubics, piecewise quartics, piecewise quintics. It turns out all we need are piecewise cubics. These points where the polynomials are tied together are called knots. Okay. Complexity will be dictated by the number of knots. Complexity is dictated by the degree of the polynomial. Complexity is dictated by how many sine and cosine terms we need, and so on. And so what we're going to do is we're going to move to these approximations, but they're all going to be linear. We're going to talk about when they work, when they don't work, and that sort of thing. But you're going to go, well, I have too many of them. Which ones do I need in there? And I say, well, why don't you do a lasso? That is, that's exactly what the lasso was developed for. Let's take out the things we don't need. And so, again, that will simplify things. So here we're going to approximate nonlinear things with expansions that are linear. We're going to have an approximation error that's going to be in epsilon. We're not going to worry about that very much because we're going to have lots of observations. But we're going to have a huge number of terms here. And then how do we get rid of a huge number of terms? We do a lasso. Okay, so that's what we'll be heading next time. I believe that's chapter 7, moving beyond linearity. We'll also talk about so-called generalized additive models. I might talk a little bit about projection pursuit. But one of the things I want to point out here is everything's coming back to linear models and lassos. And you're going to see this recur now throughout the course. Okay? That is, we'll have something that doesn't look like it is at all linear. And I will set it up in such a way and say, you see it's linear and it's really complex. How do you handle things that are too complex and they're linear? And you go, oh, I must be able to do a lasso or something similar. And we're going to find that that works up until we get to neural nets. Alexa, off. The Alexa team was one of my teams, so that's one of the original Alexas. She's really clunky. Okay, so that's it for tonight. I will see you next time. I'm having office hours now. Some of you came to office hours. It might help if you sent me an email if you're coming saying, I want to talk about this, because 2 of the people, in fact, all 3 of the people that I talked to today wanted essentially to talk about the same thing, and we could have done it all in one fell swoop had I known that. Why don't we try to do that? Just send me an email. I want to talk about this. And then I will ask people's permission. Whoever's there's first gets to say, no, I don't want to talk with anyone else. And that's fine. And I'll let them in, or he or she can say, yep, it's fine if somebody else joins in, and and we'll do it that way. Okay, see you next time.